All right, welcome to the Transformers Recitation Part 2. Um, this will be in continuation uh, from the Part 1 where we coded it from scratch. One thing I'd like to note before we begin is I reviewed the recitation that I'd recorded before, and I think I spoke very slowly in terms of my pace. So please feel free to 2x this and watch it. Right. So I'll just go over the architecture once more, so that because the vision transformers, and so in this part we'll be focusing on the vision uh, uses of the transformer in computer vision, and so the architecture itself doesn't really change a lot, and so I'll just review uh, what we did in the recitation and the two lectures before, just in case you've been busy and not looked at it, so that it's useful. So if you remember, this is what the transformer architecture looks like. You have your input embeddings coming. So this is the encoder block. If the input embeddings coming in, there's a self-attention block here. You attend to the uh, different parts of the input. So in language, you basically have a sentence, and you're attending to different parts of the sentence uh, throughout the sentence, and then you pass this, and the final features from here go into the decoder block, which has the output embedding. In our case, we were actually using so this was trained for the next word prediction task. Though this will change with vision, and that's one of the interesting parts, like what have the researchers done in this aspect. So you get your input from here. You have a self-attention part here first. It's generally masked, right? um, and in this case, you had your key and value come in from here, your query from this part, and that's why this was a cross attention block. And then you pass that, and there was a final classifier layer for predicting the word. So let's begin. Okay, so for the vision part, we'll be covering VIT, DTER, and language will be next recitation after that, depending on when we get time. So because vision was the most popular one, we'll cover VIT, which is the vision transformer, and DTER in detail. So let's look at them. So this is from a survey paper on use of transformers in vision. So some of the places where some of the architectures which were useful were vision transformers, uh, which is kind of the one which broke the field in terms of the fact that they didn't use any CNNs at all. The SWIN as well, which I'll just briefly mention later on. And then for object detection, there's DTER, which is from Meta and did quite well, because they basically show how a transformer can be used for object detection, and the way they train it is quite interesting. All right, so it's called VIT. It's basically vision transformer. The paper comes from this paper, and image is worth 16 cross 16 words. This is quite interesting. Why is it 16 cross 16 words? So that's basically a 256 dimensional feature, and transformers for image recognition scale. So if you see this, you have the transformer encoder, and what's being passed into the network is basically patches. So the reason why they do this is, let's say, and that's why we reviewed it initially, was what was being passed into the transformer for natural language tasks were sentences with words. But if you were to now use images for the same task, how would you do that? So you would ideally want to break the images, because you want to you would want to attend some part with the other part. Now, which parts would you attend to? Would you attend to pixels? In which case, depending on how large the image is, your 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 input would increase significantly. And the reason why that causes is, that the reason why that causes an issue is your um, attention module is basically big O of n square. So because of the compute effectively increases significantly as your length increases, on the order of n square. So what would you do? So the authors here suggest is you basically break it down into 16 plus 16 uh, patches of 16 plus 16. So your input actually becomes a 256 a 256 dimensional vector. So the way they do this is they basically pass these patches and then do a linear projection of the flattened patches. So they first flatten this, unroll it, and then they pass those flattened patches. And with those flattened patches, they uh, concatenate the position embedding, just the way you had it uh, with sentences, except here they're concatenating instead of adding. Um, yeah, so the main reason this is being done is it's because it's the images can, so images could basically be thought of as sentences, and that's what they're trying to say here. And the way you want to think about the sentences, you want to break it down into smaller parts, and the smaller parts here become these 16 plus 16 patches. You could um, you could also think of it as doing global attention instead of local attention. So instead of attending each small part with a different part, what you're doing is you're attending these bigger parts directly with the other bigger parts of these 16 plus 16, and that is being passed after this to the transformer encoder. The transformer encoder is actually the same as it was before, and after that you pass it to the what you're doing here is something called a CLS token, which you have with sentences also. You're passing that CLS token, the embeddings that attend to that CLS token, to the MLP head, which is then used for classification. So let's look at this in detail. Right. So now you have these patches, and you then flatten the patches. You flatten the patches and add the weight matrix. Linearly project the linearly project using the weight matrix, and then add the positional encodings to get a final patch. So these are the patches that you'll then pass to your encoder, right? And now from the output that you get, you actually use the so this in this output, you're basically passing this something called a CLS token, which is basically, you can just think of it like the start of sentence token. Basically, you're trying to see, because that token itself doesn't have any value, you're trying to see what does it attend to the most, and basically through that you're trying to see what does the image attend to the most in the given image. So it could be the trees, it could be the building itself, the structure, and one way to look at that is through the CLS token. And that's done a lot with language tasks, and that is where this idea came from. So this is basically what is done in the VIT paper, and if you look at it, it's quite simple. They haven't really changed the architecture at all. It's just the way they're treating the images and how and then the attention between these parts. So nothing really extraordinary being done here, but the fact that they're not using a convolutional network is was quite revolutionary, because till that time it was just convolutional networks or convolutional network based features being passed into transformers. But what they really showed was that you could get it to be as good as um, you could basically outperform convolutional networks by using the vision transformed. However, if you have now done homework to part 2, you know that Connext actually came after this, uh, and their entire claim was that if you use the strategies that you use for training and transformers, you effectively beat them. So that was another ablation study. So there's nothing really conclusive here which says that, oh, transformers are better than the convolutional networks, or convolutional networks are better than transformers. It really depends on a lot of factors, which you have probably realized by the time since the course is almost coming to an end. You probably know that there are a lot of factors which which basically define how well your network performs. So um, so this actually brings us to the next part. um, Before we do that, let's just look at this part in terms of why attention is better than convolution. So what this graph is showing is, uh, depending on how deep the layer is, it shows how far your network can attend to the other parts. So when you have a convolutional network, what you'd effectively see is something like this. Basically, unless your kernel sizes are really large, your network initially will not be able to attend to parts which are really far away. But attention right from the beginning can do that because of the fact that it has attention. So this is why attention performs really well, even with networks which are not very deep, as opposed to convolutions. So this kind of shows, and if you remember, convex really performs better when you have a, quite a deep network, while transformers are not that deep. You can, I mean, this LX can be changed, but still, compared to convex, a lot less deeper. Um, yes. All right. So from now, from this we can actually move to the DETR architecture. All right. So this is for object detection. What this paper really talks about is how you can use a transformer based architecture in conjunction with a CNN uh, front end to detect objects. And the way this works is, so you have these birds, and the network effectively predicts uh, these set of box predictions, which are, let's call them n. In the original paper, there are 100. So no matter what you give as input, this network will output 100 predictions, right? So with these 100 predictions, what each prediction is basically, maybe I'll draw this stuff. So what each prediction basically gives is the class and the bounding box. So you could have, since it's 100, in this case, it would be some two of them. For the trained one, there would be, for two of them, it would give the correct class. And for the others, it would give no box. So it would still be outputting these 100 outputs with some bounding box as well, but it would give a no class output. So if you see this no object, yeah, so this no object is phi. So let's now come to the training of this. So the way this network is trained is because you're basically doing um, a object detection task. There are a lot of things that come into question here, which is there an object? What is the object? Where is the object? And it does so by using this bipartite matching loss, right? What that does is, for any box, you basically try to find the box that matches it the closest, and you're only doing a one-to-one correspondence. So you're not matching each box with multiple boxes. You're just matching one box with the, so on the right is the ground truth, on the left is what you predicted, and for each box you try to find one box that matches it. And for that box, you then have a loss function, depending, because you're, so based on the channel and bounding box, we'll come to that. You have a loss function, and then you try to minimize that over uh, all the n observations. So let's look at this in detail. So what you have is, it's also called the Hungarian matching algorithm. The way it works is, there are some others also. If you're interested, you can look at them. What this does is, you have this initial loss, which is basically based on the classification. So this is a cross entropy, but based on first the matching being done. So this is the matching function. I'll not go into detail in this. Based on the matching, you basically get a one-to-one correspondence for each of the predictions. After you get that, you do a cross entropy loss on the classification itself based on what is predicted and what the output should have been. And after that, you do, if it's not a if it's not outputting something being no box, right? When it's not, when it says that there is actually something, you also look at the bounding box loss. And the bounding box loss is actually a weighted sum of the intersection over the union and the L1 loss. So the intersection over union is quite a famous loss function. I guess most of you might have heard of it. In case you haven't, I'll just let you know what it is. So in this case, let's look at the intersection over union. It's generally not how this is done. It would be for the same box. So let me just draw that. Let's say your predicted box was this, while your ground truth box is this. Your intersection over union becomes the intersection over the entire union. So that's it. Maybe I shouldn't have even done that. Yeah, but anyway, we'll move from here. And the other loss is this L1 loss between the bounding boxes. So depending on how you define the bounding boxes, it'll be a 4-dimensional vector. You do a L1 loss on that, and that's your loss function. So what I've done till now is just talk about the loss function. We haven't really gone into the network. Let's go into the network now. Right. So from the CNN, you'll get this set of image features, and what they actually look like is basically you'll get some M channels of height, comma, width, right? So this is what your dimension will be. Apologies for my handwriting. You get this, and then you add the positional encodings to that, and after that you'd flatten it. So you'd flatten it to this. So now you get vectors for each channel. You get some height cross width vectors, or you could also think of it in terms of this. And then you pass these to your transformer encoder. Let's just look at the encoder also. My bad. Here we are. So this is the encoder for the Dieter paper. It's basically like the encoder that we had for transformers. Same goes for decoder, although the way the decoder functions is different. So you have the same encoder n times. This block of channel height cross width is then passed into this transformer encoder, and you get the same number of outputs from the encoder again. This is then passed to the decoder the same way you did it with a normal transformer for cross-attention work. So this is then passed to the transformer decoder, and the transformer decoder actually has these inputs being object queries, right? So for the sentence task, we had masked inputs being given in, and then we had a final classification. But here you have object queries coming in, and you have object queries being sent out. And these object queries are basically then passed through a feed-forward network, and those give you the outputs. So there are 100 of these. So this is actually some n cross 100. This is also some 100 object queries, and you get hundreds of these. I'm sorry, 100, just 100 of these, because that's the number of outputs you're given. So no matter what your input is, it's always going to send out 100 outputs. So if you had, let's say, 100 objects in this, it could classify those 100 objects theoretically. So the question here is, what are these object queries? When you send them random object queries, but the goal actually is to learn these object queries. And what I've plotted here below are from the paper, the object queries, the learned object queries. So what they're doing effectively, these are 20 of them, I guess, 3, 6. Yep. So what they're doing is they're attending to different parts of the network to see if there's an object there. And that's what you do with these object queries. You learn the object queries itself also. Um, so these are not exactly the object queries that from the attention, but think of it this way. It's basically asking for the asking the image for different parts of the image to see where does the object actually lie. And after that, it passes the after uh, the stuff is done in the decoder, which was here, which if you see is actually again similar to the decoder that we had for the um, language tasks. So this is really interesting because if you see this, it's the same structure basically which was used with language is now being used with images. And that's what vision transform is also talking about. 16, the fact that you're calling a image patch a 16x16 word. So that's something to think about, the way that this is moving around. That's why transformers are really considered something to be considered to be uh, really revolutionary, because you're now really joining both the things and using the same architecture for that. Uh, well, you were using CNN plus LSTM also, but still. Okay, so now after this, let's look at some interesting results. This is the part which actually gets it, makes it really cool, which is these self these are basically uh, they plotted the self attention block from the encoder, right? The encoded image and then the self attention block after that. So you took in the input image and then you scaled it after the attention, and you get these outputs, which are basically the part that the image pays attention to, and then you pass those to through a resonate feature, and you get this finally, which looks a lot like segmentation of different aspects, right? So there's the cow, the ground, the bush line behind it, and the sky, and that's what is happening here. So you're having you basically get a pixel wise classification here, which is just segmentation. So you're using the same architecture and using that to do segmentation. This is another cool image. Basically what they've done is they've taken the self attention of the images, the image blocks that is output from the encoder, and try to see what the image really attends to. And what you see is it's attending to different parts of the image, which are the cows in this case. And if you go below, okay, sorry. So what you see here is basically the fact that you can use this architecture to do classification and pixel-wise classification and object detection. There's something else I would like to show you guys, which is this. So what you can see here is, this is from the same paper. What you can see here is so because it's outputting multiple objects in those 100, it treats them, so it's basically giving out 100 outputs, right? And for those 100 outputs, there's one box which is of the class elephant, there's another box which is of the class elephant, and it can actually attend to different parts of this and know that this belongs to the same group and this belongs to a different group, which is really cool. You can see that same way here. So it can really figure out which part belongs to uh, which which part belongs to which predicted output. So yes, so this is DETER. I've rushed this because, I mean, when you go into detail, there's a lot of that. I briefly wanted to mention, really briefly, some two other architectures as well, which you should know about. So there's this Swin transformer architecture. And what happens here is, what what they're basically doing is shifted windows. So they're doing something like strided convolution. They break it down into different parts and then do a strided convolution on it, and then use those to pass them into transformer. But what Connext basically showed is that it's better than Swin transformer and Vision transformer. So if you want to do object classification using convolutions, feel free to using Connext, feel free to do that. And there's this newer transformer called Perceiver. What that basically does is it's for multimodal stuff. So one of the issues that you face with transformers is because it grows by big O of n square, you can't really give in bigger inputs. What they try to do in this architecture is basically try to beat that by just passing the inputs as keys and values through cross attention, and then pass the output from that into the latent transformer. So they try to solve the issue of uh, large large inputs. Yeah. So these are the two. Feel free to ask questions on Piazza. That's about it for the vision task. For the language task, we'll probably record something later. Right. Thank you, guys.